What is up, ladies and gentlemen? Welcome to another exciting episode of the True Earth Debates. We are super excited to be joined by two wonderful guests. We have Dave Weiss from deep inside the rabbit hole, as well as Mr. Joel. We appreciate your guys' time. Let me go ahead and bring you into the show and get things rocking and rolling. Thank you all for joining us over on the YouTube and the Rockfin. We have quite a few legends over there as well. Can't shout you out, until you chat it up, but not everybody's comments makes it up, as you know, for those who have been here. For those who are new, that's just how it goes. So click the link in the description if you'd like to support not only myself, but tons of other content creators as well. So only one way to know, and that is to go. So let's go ahead, pull you guys in for just a second. Awesome. Welcome to the show, Dave. Thank you for joining us.
What's going on? This is going to be fun. And Joel, thanks for coming.
Yeah, it's going to be fun. I'm looking forward to it.
For those of you that are like, this guy looks familiar, let me just give you a quick rundown. Sean Hibbler and I had Joel on was it a year ago or how long ago?
Yeah, almost a year ago.
So a year ago, and first I want to apologize, Joel, for any comments in the chat that are mean. It's just we have a lot of passionate flat earthers.
Yeah, I know. I respect it.
And the way that we see your beliefs, people get fired up. So everybody, Joel is not a shill. He's not a troll. He believes what he's saying. And he's, we see the world completely different, but he's a good guy. And we're going to try to share some information and see who learns something tonight. Maybe it's us, maybe it's him, maybe we both learn something.
Hopefully it's both. Yeah.
Yeah. So I have a couple quick rules, and you're already off to a good start. You need to smile at least 3 times, and you need to crack at least 3 jokes. Or it's sure 2 or 3.
I'm sure we'll surpass both of those. It'll be fine.
All right, good, because you were very, very serious last time. Very serious.
Yeah, it was the first time. So.
All right, good. I'm happy to hear it. So,
all right.
Skylar, anything you want to start with to say, or we'll let Joel kick it off? And also last time I did listen to our interview, and I had warned you that we were going to interrupt you a lot and talk a lot, and we sure did. We're going to try to not interrupt you too much today.
Likewise.
All right.
So you're Skylar? Sorry,
Yeah, it's all good. Joel, we just met, so it's nice to meet you. Thank you for giving your time and attention to this very important matter. I feel like the True Earth debate is probably one of the most, it's starting to be the shoe on the other foot, right? But it was for a long time one of the most underrated but controversial conspiracies out there. So controversial that even the YouTube heads got pulled into Congress and said, well, what are you going to do about the conspiracy videos, the flat earth videos, and so on and so forth? And so now we have seen the results of that with a completely stacked deck as far as the search algorithms go. But neither here nor there. It's nice to meet you. I run the True Earth Debates. I'm also on Dave's team here. I believe we're on a stationary plane with topography over top. We actually build all of our useful data about the Earth off of a flat plane. We have the sea level. We have sonar mapping the oceans as flat. We have, as well as radar waves going over 10,000 miles. Lots of other evidences that seem to indicate that, there's no curvature in sight. So I'd like to go ahead and pass the floor over to you. What do you think is the biggest reason why you believe that you're on a spinning space rock?
The biggest reason?
Oh, hold on. Dave is muted.
Yeah, you're muted, Dave.
Yeah, hold on.
I do that once every show. Just Joel, we asked Joel to do them. Last time he said, I'm going to go do the math. I'm going to come back. And he came back and said, hey, I want to talk about these 3 things. And I agreed that we're going to talk about those, but then we're also going to talk about others. So Joel, you can answer that question right now if you want, or you could start wherever you want. I want to make this I want you to lead the conversation.
Well, in good faith of, I guess, following on from our last discussion, and this is sort of like a sequel, if you will. Like you said in the last interview, you guys hit on the inverse square law a lot, because I was bringing up math a lot, and you were like, well, if you like math so much, it doesn't really work out with, us being able to see Polaris. It's way too far, 431, 433 light years. So I was like, okay, I wrote that down. I said, I'll do the math, and I did the math, and I wanted to share it with you guys, if that's fine.
Sure.
I wrote up the little paper here. It's only 4 pages. It's not crazy. It won't be
4 pages.
Yeah. No, well, it's because it's a lot of diagrams. So like visuals.
I got it, but I have a question for you. How do we know that Polaris is 433 light years away? And I believe mainstream science is trying to decide if they need to subtract 100 light years from that number. So to me, in my world, the way I see it, it's a made up number.
Well, that's going to be off like spectroscopy and things like that, and chemical makeup and maturity of the star and things like that. So we can measure the type of light that's emanating off of it, and then we can basically figure out how far it is from that. That's one of the ways anyway. But right now we're kind of just giving the 431, 33 light years somewhere in there as a given. So if it's all right if I went through this with you guys, it's not crazy or anything. The craziest part about this is unit conversions. That's it. Like converting light years to meters and things like that. So
I'm going to do my absolute best to not get mentally fatigued.
Okay, I'll try and go quickly. It shouldn't go too much longer than the intro.
Touche. There you go. It's one. You're good.
Alrighty. Can we see this? Is this seen?
Yep.
Okay. All right. So I wrote this. So I'll just sort of paraphrase through it. The question is, with the inverse square law, how are we able to see the North Star? Okay, Polaris. So the way that we kind of understand it, we have a point source of light like a star, and you can imagine that light emanating off of it, in sort of circles, like spheres coming off of it. So we're interested in the intensity of light at any distance from the center. And so we would have to know the surface area, the area of these spheres, of any one of these spheres, like however distance you want to know, which is going to be given by the radius. So in this case, the center's there, radius is the distance, and the surface area is the area around the sphere. So this is basic formula, like first grade math kind of stuff. So the inverse square law is basically this.
I think first grade is a bit. I definitely didn't learn. I definitely didn't learn this in first grade. I'll just say that.
Well, I just meant like formulas for like basic formulas, like volume, area, perimeter, surface area is one of those. Is what I meant. So 4 pi r squared. And so, all right. So this is kind of what's happening. So imagine these are the different spheres here, right? And so, like you were saying, Dave, the further away you get, so at 1 distance away, you have a certain intensity. Then you go 2 times as far away, you have a quarter of the intensity. And then 3 times as far away, you have a ninth, and so on and so forth. It's kind of, it's just a simple. And then this graph here kind of displays that relationship. You've got distance on this x-axis here, and then the intensity here. So you can see 2 times as far away, a quarter, 3 times, 4 times, and so on and so forth. So it gets dimmer, obviously, the further away that you get away. The big important part here to realize is that the further away you get, the less difference there is in brightness. So yes, it gets dimmer, but the amount that it gets dimmer is a lot less the further away you get. So the example I gave here, say you're like 10 times as far away, you'd see 100th of the brightness, or 0.01. Whereas if you're only 9 times as far away, you'd see 181st, or like 0.0123, which is only a difference of 0.0023. It's not that much of a difference if you're 9 times as far away or 10 times as far away. And the further away you get, again, like the less difference there's going to be between those brightnesses. Okay, so that's the big point here.
At what distance do we start to really notice that relationship?
Well, that's what I'm saying, that the more distance there is, the less you're going to notice that relationship. So David, you're muted again. Sorry.
Thank you. That's 2. I'll do it one more time. So you're saying that something is a ridiculous distance, like 100 light years. Long before you get to that 100 light years, you're saying that the difference between like 20 light years and 50 light years isn't very much. It isn't as big of a difference as the first few steps. Is that what you're saying?
Exactly.
Okay,
that's correct.
So something's 100 light years away. then can you see it at 200 light years, or it remains the same intensity at 200 and 300 and 400 light years? It goes to a point where it stops getting less. Is that what you're saying?
Well, sort of, yeah. So well, there's not going to be a point where it stops getting less, but because eventually, you know, obviously it's going to be past what you can see. It'll be too dim. So, but there's also nothing obstructing the light from getting to our eyes. Like, for example, in some of the stars in the core of the Milky Way here. Oh, it's this way. So a lot of these stars here, you know, they kind of just look like a haze at this point because they're really far. You can't see individual stars with your eyes, but you just sort of see this haze. So the light's still getting there, but you can't make out the stars themselves, the pinpricks, if you will.
Well, the only problem with that, just to interject for a moment, is that normally when you have something that's too far away to see that it's like pinpoint, right? When you zoom in on it, you're not going to be able to make it bigger, right? At least not with not unless you have an intense, like a ridiculously intense amount of zoom, right? Most of the time, you would agree that you're not with like a camera, right? You're not going to be able to zoom in on something that's, you know, 400 light years away. You know, if we're seeing a pinpoint source, right? Would you agree with that? That we're not going to be able to zoom in on that with a P900?
To a degree, yeah. Essentially, you can't just get a whole bunch of detail out of something unless you're closer to it, you know. So if you're really far away from something, you can only zoom in so much. So yeah, I agree with that.
Well, it's actually it's not just that, but it's also the actual size of the thing that you're talking about. So there's a point where you're pretty much only seeing a point source of light, and then there's almost no difference between 200 and 400 light years. It's basically the claim that you just made in the simplest terms, right? So if that's the case, then when you have a star that's 400 light years away and you're seeing the pinpoint source, zooming in on it a little bit is not going to it's not going to bring that size back in, right? It's not going to get larger by zooming in on something that's okay. Thank you.
Yeah, that's relatively accurate. Yeah.
Okay. So the problem is that we have tons of videos of people zooming in on stars and they get bigger every time. So, and that's what P900.
That's a slightly separate subject. Let's go ahead and just finish this off, because the second part of this, I explained the concept, and now I plug the numbers in. Is essentially what's happening here. And then once we get through this, then we can have the discussion. All right. So I said let's try. Let's plug everything in. So there's a couple terms here. So what we were looking at here, when we're looking at like the area, this is like square meters, right? You have a meter here and a meter here, so it's square meters. That's actually going to be called the flux. So that's the astronomy term for it. And then luminosity is whatever the star's wattage is, output. So it's the same thing. The inverse square law is the same thing. We have luminosity here, and we're trying to get the flux. That's basically like if Earth was right here, you want to know how much light is sort of like at this sphere, at that distance away from the star. So that's the flux. So all we need to find is how bright the star is and how far away it is. So its estimated Polaris is 25,000 times brighter and 50 times larger than our sun. All right, these are estimates, but we know the luminosity of the sun is this. So I called it L Sol. So all you have to do is times that by 2,500, because it's 2,500 brighter. So we multiply that out, we get our luminosity. So this is the supposed wattage output of Polaris. So we have our L. And then here it's 431 light years I put here. You could say 433. It's going to be kind of negligible at this point.
Would you agree that this is all theoretical?
No, I wouldn't. A lot of these are hard numbers. So
which one would you say is the hard number?
Well, certainly the luminosity of the sun.
How did we get the luminosity of the sun?
You can measure it with spectrometers and with light measurements, essentially. Like you can measure how much light is hitting a sensor.
Okay, that's
Joel,
fair.
do you have any examples of anything that's twice as bright as the sun?
I mean, there's plenty of stars. Like stars.
No. When you look at a star, you can theorize that it's whatever number brighter than the sun. But do you have any examples around here of something brighter than the sun? Twice as bright.
The issue with that is the sun is giving off all wavelengths on the electromagnetic spectrum. So I could find something that's brighter in the visible spectrum, but not
So
like on all wavelengths of
I find
radio
it hard
waves and everything.
to imagine something
Well,
twice as bright as the sun. But let's just go 10 times as bright as the
I don't
sun.
think
10
there's
times as bright as the
anything.
sun.
I don't think there's
I don't
anything
even.
brighter than. I don't think there's anything even visibly brighter on the visible spectrum brighter than
But
the
let's
sun.
just say 10 times. Let's just pretend that we can do something 10 times brighter, which is unfathomable to me. And you just carefully, because you're doing some equations. Equations are not empirical evidence. Saying this star is 25,000 times brighter than the sun, and you just roll it off like it's a fact, but you have zero evidence of that other than it has to be if you pre-assume space is real and stars are far.
Well, I also wanted to get.
Not necessarily, because there's neutron stars and there's very dim stars as well.
But I wanted clarification on, are we talking about the sun's apparent brightness, like its visual brightness to us, or are we talking about its actual, like
Its actual brightness.
Okay,
Yeah.
so how did we get that compared to its brightness to us?
We sent probes into it. So I know you don't believe that, but that's how we got that data. That's why it's.
Do you
So
have any
important.
evidence of those probes going to the sun?
Yeah, you can look it up. I don't know what their names were.
You can look it up, and it's written by NASA. I believe last
No,
time
I think that was actually a Russian probe. Was the one that went to the sun.
not Russian,
That's even more
China,
trustworthy.
Japan, NASA.
Well,
it's
I mean,
all the
you
same.
gotta.
We don't have to believe the story about Narnia.
No, you don't. That's what I'm saying. Like, I could say these things happen, but it's kind of hard because I know you guys don't believe it, but that's like, what am I supposed to fall back on, I guess?
But that's
Well-
kind of
well,
where
what
our
you're-
problem is that we're looking for what we can actually verify, and we're always having to rely on these stories from the accused, right? And so it's just not. I mean, it's really not very good optics for the globe model.
All right. Well, let's just continue. So we got to find the distance now, right? So we only have 431 light years, but our flux measurement is supposed to be in watts per square meter. Okay, so we can't use light years. So I converted light years to meters, and then 401 light years is this many times that many meters, which are how many is in 1 light year. And so we get the amount of meters. This is how many meters away Polaris is. So now all we do is we plug that in, we get the luminosity of Polaris, and then we get the distance. All I did was plug those in. This is the luminosity and the distance, squared the distance, multiplied it by 4 pi, and then I divided them. And I got this really tiny number, right? So 4.61 times 10 to the negative 9th watts per meter squared, which is really small. That's this many zeros. The sun, for example, is 1400 watts per square meter. So that's in the positives, that's not in the positives. That's past the decimal point. That's 1400 watts per square meter. This is 0.0000, like really, really small. And so for a comparison, and by the way, the human eye, the lower limit is in the magnitude of 10 to the negative 10. So anything below 10 to the negative 10, our human eye wouldn't be able to pick up. And then another reference is one foot away from your average candle, which is how we get luminosity measurements as a standard. That's going to be 0.01576 watts per meter squared. So it's still pretty small. It's a small, it's a relatively faint light. So then I looked at all of these other stars. So we have Sirius, which is the brightest star in the sky. It's only 9 light years away. And that's still 10 to the negative 8th. And you can see that sort of relationship here of how they're not that different. It's because we have 10 to the negative 8th, negative 8th, negative 8th, and negative 9th. With all these different, Rigel, I never know how to say that, 773 light years away. And that's still negative 8, while Sirius is only 9, and it's still like negative 8. So you have a bunch of different variables in size and intensities. But you have Polaris at 431, and it's only at negative 9, and that's above our limit of being able to see the star. So with all the numbers, with the distance, and with the size, we would be able to see Polaris with the inverse square law, and that's essentially kind of how the numbers would work out. We can now have discussion about the sources of that stuff and all of that good stuff, but with the numbers that we purport to have now, it does work out. it's not
So,
against it.
so I'll throw something in, and then Scarlett, you can go. Everything that you're telling us is you're great at math, by the way. You're awesome, and great charts and everything. And I could actually show you a chart of an unknown island off of Japan, one of the 7,000 that they just found. And there's an amusement park there with the biggest roller coaster in the world. And I could show you the coordinates for that. I could show you how far it is. I could tell you the specs on the roller coaster, the G-forces. I could show you all of the building plans, everything all about it. And everything will add up no matter how you look at it, sideways, forward, reading it, upside down and backwards. Does that make that amusement park on that island real? Or is it just theoretical, right? So everything you're talking about is theoretical. You're pre-assuming that space is, infinite and expanding. You're pre-assuming that those lights in the sky are billions of miles away and 25,000 times brighter than the sun, to me, which is absolutely insane.
2,500.
2,500. Well, if it was twice as bright, that's still insane to me. And so this is just a quick quote. All of the theoretical work that has been done since the 1970s has not produced a single successful prediction, says Neil Turk, director of the Perimeter Institute of Theoretical Physics in Waterloo, Canada. That's pretty intense.
Well, what about all the theoretical work done before the 70s?
Like what?
Like general relativity.
I'm not a fan.
That's the big one.
Not a fan.
Yeah, so actually about to, there's a big discussion on upending general relativity amongst even mainstream physicists. It's actually, when you look at that coupled with Big Bang Theory and what they've been teaching in the mainstream schools, there's actually 16 predictions that the theory gets completely wrong. And the James Webb Telescope has actually only apparently furthered the mystery. I know for us it's like a catch-22. We don't believe in the James Webb Telescope, right? So why are they, spinning these different narratives? I think it's for confusion. But in any case, even if the data is real, right, the data is not lining up for the expectations of general relativity. But again, that's kind of a different topic than the discussion of the stars. When we my
main point was just because a majority of the last interview was saying how the inverse square, we shouldn't be able to see Polaris. And so at least with the numbers that we have, we would be able to.
So I mean, theoretical numbers, you're making a statement that
they're observations.
Hold on, you're not making an observation. You're making a statement. Hold on, that light, the light of a star will get dimmer and dimmer fast, and then it gets less dim and less dim, and then it just travels forever and stays at the same brightness. You have no evidence of that being real, and logically, it doesn't make any sense to me. But you have no way to prove that's real. That's just a theoretical statement that has to exist for your infinite solar system, infinite galaxy, and universe to exist.
I'm not sure that they're infinite. I'm not sure I believe it's infinite.
Well, expanding, very large, bigger than the flat Earth concept, if you will.
Sure, yeah, it's definitely bigger than that.
Right. So you're reaching to places that you can't verify. You can just read books and trust government agencies. They're very trustful entities. And you're not looking here on Earth where we can actually scientifically prove that we're not a globe. I mean, you want to believe that Polaris is 2,500 times brighter than the sun, which that's crazy. I mean, if that was the case, there's other stars that are probably 100,000 times brighter than the sun, or 1,000,000 times brighter, right?
Not a million. I don't think a million.
Okay, yeah, but
many magnitudes, yeah.
But these numbers that you're coming up with, but they all kind of look pretty much the same. And when we zoom in on them, they all
that's proof of the inverse square law to me. I think that's proof of the inverse square law that the further away
they all
things
look the
get,
same. Everything just evens out.
Well, in our local celestial neighborhood, yes, but like once you get further out, like out to the middle of the galaxy and stuff, things look a little different. They get denser and they get closer together, and they get into you have nebulae and everything like that. So, and then you have other galaxies, and then you can zoom into and see specific stars in other galaxies.
Do you believe in the James Webb Telescope?
Well, yeah.
Okay. So the James Webb Telescope, it finds a spot called Lagrange point 2, and that's where the gravity of the sun and moon and the Earth, and it just finds that perfect spot. Okay.
Yeah, it's a saddle point. Yeah.
So over the course of 6 months, the sun and the distance between the Earth and the sun change. I had all the numbers before, but as it changes, it would have to move like it's in a tractor beam. Okay, it would have to move, and it's moving like very fast in two different directions, throughout the year towards the sun and away from the sun. And you're just believing that tractor gravity is holding it in the perfect spot. Here's my question though. If you watch the launch, did you watch the launch of the James Webb?
Yeah, I did.
And it was over Earth. Maybe this is, that's not it. That's me making a James Webb image. Let me just find something here for a second.
You're good.
Where is it? Here it is. I think this is it. So this is the launch. Let me just see if this is the video I want. And it's up in space. And then is it deploying here? All right. So it's the next one. You see, this is it. So here it is, and they're showing us this beautiful curve of Earth. They always show us this beautiful curve of Earth. So it's ejected it here. Now, how many miles away from Earth is that? Is it 1,000,000 miles away? It's not 1,000,000 miles away. It's a couple hundred miles away, right?
Yeah.
Let's round up to 1,000. Let's say it's 1,000 miles away. Got a great shot of Earth. Somehow we can see through all the atmosphere and see the perfect edge of this. And here it goes out here, and it's going to deploy. Let me just jump forward. It's gonna and if you watch, the signal's breaking up here, and it's only 1,000 miles away, probably a lot less. And it's going away. It's already ejected from the rocket.
Yeah.
And I'm going forward, and it's out. It's now putting out its solar panel.
Right.
How does it go park itself 1,000,000 miles away? What gets it to the Lagrange point?
Well, that's literally rocket science, man. I mean, that's orbital mechanics. They exceeded the escape velocity of the orbit, and so it was no longer within the.
So you're saying the rocket is in orbit and it pops the satellite out, and then that satellite knows to go 1,000,000 miles away and park itself. Is that what you're saying?
No, not necessarily. It doesn't know to do. It's.
How does it get there? How does it get there?
I think you need to know that it's constantly correcting itself.
How does it correcting? Does it have engines on it?
No, it's got I don't know what the nozzles, pressure nozzles. I don't know what they're called.
So the satellite has pressure nozzles that are pushing against what? What are they pushing against?
You don't have to. It's not the pushing against. It's the fact that it's pushing something of itself out. So it's equal and opposite.
And what is it pushing out? What is it pushing out?
Pressure, air pressure.
Gas. It's pushing air out.
Gas.
So have you ever seen where we take a vacuum chamber and we put a little rocket and a fan and all sorts of stuff and nothing moves? We just light it and it won't. There's no propulsion. There's no pull. There's no push. We hang a feather in front of a fan and there's nothing. There's nothing. So we could argue that all day. It doesn't matter. Yeah. You're saying that this thing with where are the thrusters on here? If you take a look at it, I don't see.
I think I can actually see them right there. There's one at every corner. At every corner.
So those four are going to take it out of orbit and park it 1,000,000 miles away. That is a faith. That is a religion.
I have another big question. Big one for the
think
thrusters,
it's just math,
right? Well, I'd like to see you try to use math to get out of this one. So we know that there's something called back pressure. That's how all our pressurized systems work when we're dealing with gases with the pumps, right? So we have atmospheric pressure pushing down. Without that, the gas will escape the pumps, right? So out in space, there is no back pressure. So what keeps the gas from escaping?
Gas from what?
The thrusters.
Well, they're nozzles. They open and close.
Yeah, but see, okay,
it's like it's a container. They're contained inside of the thing, and it pushes it out. And it's like if you were to blow in space, I guess. It doesn't mean it's just gonna deflate immediately.
Can I ask what right here? They're having this bad video feed. Is it going to get better as they get farther away from Earth? Are they going to be able to transmit some high-res pictures because they can't seem to transmit a picture here?
Well, I don't think the craft, the rocket, followed it. So, I'm not sure what you mean.
So the transmitter on the telescope is better than the one that's on the rocket. Is that what you're saying?
Yeah.
I'll go with that. Yeah.
Yeah. Well, I think we could go ahead and move to the next thing I wanted to talk about, unless you guys had something
No,
specific.
we'll go to the next thing. And
I,
Skylar.
I still had one thing on the stars too, because my point
Sure.
on the fact that we can zoom in on all the stars and they all increase in visual size in the camera lens is evidence that they can't be at these varying distances of vast light years away.
So I'm not sure. I'm not sure what footage you're talking about. For
Amateur
that,
footage.
that's not just blurry.
There's hundreds of.
Besides blurry,
But
but
you could just call it. I mean, I understand that you can just call it blurry, but even the blur, right? It's getting bigger in size. Like that wouldn't happen. It's a point source of
here,
light.
so I'd encourage you to take a similar camera or to ask someone to do this. Take whatever camera that you did that with a star and do it with like a different type of smaller dim light. Put it off in the distance in a dark area and zoom into it, and it's gonna look the same because it's a blurred. It's so exactly how you described earlier.
So
Remember how you were
well, when you do it here on Earth, the diameter of it is, or not the diameter, but the actual angular size of it is going to increase, right? Of the actual thing.
No, it's
The
going to
blur
get
and
blurry
the
like he's
object.
showing that. That's blurry.
That's
Not,
blurry. Looks pretty sharp to
yes.
me.
No, that's what happens when you sort of when your camera zooms in too much that it's not able to actually process the light appropriately. So all it's getting is just a bunch of random protons that
You know,
it's
you
not
could see this
focusing.
with your naked eye. You could see this with your naked eye. You don't even need to zoom in to see Arcturus. You look at it on a clear night, and you can see this with your naked eye.
Well, yes, it sparkles, it twinkles because of the atmospheric distortion in the way.
The atmospheric distortion is doing this.
If another interesting, yes, an interesting way you can tell that, and I encourage people to try this as well. Look at Arcturus or Sirius or any other bright star when it's lower in the horizon, when it's near the ground, and then look at it again when it's straight overhead, and you'll notice a big difference in the distortion there, in the twinkle, if
Well,
you will.
absolutely. You're looking through the atmosphere. Everything's distorted. Look at somebody, a quarter of a mile down the beach, and they're going to be all distorted.
Yeah.
But you look at something over your head, you're looking through less atmosphere. So just because you can distort things by looking across the thickest part of the air column doesn't mean that's what that doesn't mean anything actually. But why doesn't this one look like Sirius? Look like Arcturus? This is Sirius. Why doesn't Sirius look like Arcturus? Why does every star have its own personality, focused or not?
That's a really good question, but that's kind of gets a little bit into spectroscopy because they all have different chemical makes. Obviously, it also depends on the atmospheric conditions of the day, the camera you're using, so and obviously so that top middle one, for example, is very clearly out of focus.
Absolutely, 100% agree. Let me ask you a question. They tell us that, we're looking at the star, we're looking up through all the layers of our atmosphere and all of the radiation belts and everything else, but we can tell what gas the star is made out of. How come they have never done an experiment here on Earth? Like, get a garbage can, fill it with whatever gas you want, put it a quarter of a mile down the street, and then get somebody with a spectroscopy. The spectroscopy instrument?
Yeah. Spectrometer.
Spectrometer, thank you. And have them tell you what gas is coming out of the can. No one's ever done that.
Well, that's okay. I think that's just because. So what spectroscopy is measuring is actually the wavelengths of light, and the different types of wavelengths of light will indicate different sort of gases.
So I have a challenge where we get a garbage can with a big bright light in the bottom of it. We fill it with a gas, and then we have somebody with a camera, let's say a mile down the road, half a mile, and they can tell me what gas it is. I'll point the light towards them. I'll pull the top off and let the gas escape with the light behind it. And you think that somebody can do that? It's never been done, right? They haven't tested these instruments here on Earth, and they just shoot them in space and go, oh yeah, well that's hydrogen, oxygen, and that's we can tell what that is. It's all again theoretical nonsense.
Well, the trash example is just that's not exactly what's happening. So,
well, what you're saying is you could see the light and the gases in front of the light. I'm giving you a light with gases in front of the light. It doesn't have to be a garbage can. It could be a beaker. It could be whatever you want. We can put the gas in a beaker and put a light behind it. And you think you can tell me what gas is in that beaker? I
So
say you can't.
the thing is, it's heated, it's actual gas fusion. You know, this is an actual active chemical reaction that's happening. That's the thing that's giving off the light. It's not just like a light with gas around it.
Where else do we
That would
see
be
that, and where do we see that terrestrially to be able to make that comparison?
Well, it's only with stars. You know, those are the only stable fusion reactions. I mean, unless you want to blow up an atomic bomb, you know,
So
because that's the one time that we have done fusion.
let's let's pretend stars are real and that they're spewing out gases, and then we make a device here on Earth and we can look at it and tell you what it is. How did they adjust it? How did they set it so they can know that it's right? What proof do they have that they're right? What evidence is there that any of it is right?
Sorry, Dave. That was just a very general question. I'm not sure I got the.
when they take their instruments here, the spectroscopy. I can't. What's the word?
It's okay. Just spectroscopy. I have a hard time
no.
saying
The instrument itself.
spectrometer. Yeah.
Okay. So they're taking that and they're looking at a star in the sky that's burning off gas or whatever, and they can tell what it is. How did they calibrate it? If they never did it here on Earth, they're looking up at theoretical planets and stars, and they're telling you what gases are there. It is all complete and total theoretical science. None of it has been proven.
Not astronomically, you know, like we haven't done it astronomically, but we know what types of light and chemicals give certain. We know the characteristics of certain chemicals, you know, and how they fall on a spectrum. That was a close one.
Now you can't say it either. Good.
How they fall on the spectrum, right? So you know, you'd be able to see the spikes in which chemical is what, and that's with most things. You can test that terrestrially, but then when we point it up at a star and we're sort of receiving information from that star, light, electromagnetic information, you can see where the peaks are. What
about all the gases in between that are here in our own atmosphere? It ignores those.
Well, I mean, that's why we have, you know, observatories that are actually outside of the Earth's atmosphere and things like that.
Like the self-driving parking James Webb telescope.
Again,
we're back to relying on Narnia.
It's not completely self either. I mean, you're able to calculate pretty almost exactly, essentially, of where it's going to go and how fast and all of that. So it's very.
So you have no idea how it works. You just say somebody knows. The guy in a white lab coat and a bow tie knows.
Well, yeah, I don't know everything, but I know how orbital mechanics work and how things can sort of fall into orbit, fall out of orbit, velocity.
Theoretically.
Well,
yeah,
but
ahead,
I mean, I got to be honest. If we're just slapping theoretical onto everything, you know,
hold on.
No, we don't have to slap theoretical on things. We have things that are here on Earth that we're trying to measure. That are not theoretical, but go ahead, Skylar.
I was going to say, I mean, if you're going to say that, I mean, that's kind of a cop out. We can define what's theoretical and what's, actually verifiable, right? So when we're saying, when you say the hard number is the sun brightness before, right? Again, the thing that made it the hard number was the probe, right? So we had to rely on the story from Narnia. In this case,
that's not the only thing, but that was just one example of one of the many ways we've measured the sun's brightness.
Okay, so I'm not trying to start a whole nother rabbit hole on the sun brightness when we already moved on. In any case, spectroscopy, when we're dealing with a spectrometer, right, there's obviously a big difference between pointing something up at the sky and looking at a light in the sky, right, versus actually having an enclosed environment, a lab, because most of the time when we're doing, from the experts in the field, spectroscopy is done in an enclosed environment. The spectrometer is all enclosed with known variables. So everything's known when they're attempting to analyze these chemicals. So again, we're invoking between millions, billions of miles, trillions of miles, right? Unfathomable distances. We're invoking consistent, unchanging mediums when we have no way to verify that whatsoever.
Well, the verifying is those observations. That is the verification, I guess. So I mean, I know you guys deny it, but that's the verification. Is you can take the same sorts of instruments and measure the same types of things, and you get those observations, then we get these numbers that we work off of.
So Aristophanes, with his sticks and shadows, he measured the length of the second shadow. Hold on a second, and he said, "All right, the Earth's diameter is so and so." And then later, somebody said, the Earth's diameter is so and so, and if we took a stick and a shadow and we put them 5,000 miles or 500 miles apart, those measurements would actually equal the Earth. So you're self-reifying your space with space. You're using space as your proof of space when there's no proof of space.
It's also interesting how confident you are in spectroscopy when, the people at the top actually aren't that confident. They're like, yeah, there's tons of problems. There's tons of things that we're trying to weed out. And a lot of times we do end up with unexplained phenomena. So again, you're just kind of relying on the authorities, right? Because, I'm just like you. We were spoon-fed one model. But when you actually talk to the people who are doing the work, people like George Ellis, they admit that there's a range of models that can explain the observations, but cosmology is choosing them based on philosophical grounds.
Yeah, there was a lot there, but we're both sort of appealing to some sort of authority at some point. So
let's stop doing that. Do you have was there a third topic you want to bring up, or can we discuss something else?
I've only got through one so far.
Okay. All right. I thought that was two. Go ahead.
So the next one,
then maybe we can interject after that one.
The next one was this video that I got.
I do want to shout out Karen B with the super sticker. Appreciate the shout out and the support. It does help out the channel a ton. Be sure to, if you guys enjoy this kind of content, then definitely check out the GoFundMe. We're trying to make it to Flattoberfest. There's only one way to find out if I'm an AI or not, and that's to get me to Flattoberfest, where you have a chance to shake my hand.
That is true. Joel, I don't know if Skylar's real. He could be AI. We're trying to get him to Flattoberfest. You should come to, where do you live? You should come to Flattoberfest. It's in Las Vegas in October.
Oh, I'm in Ohio, so it's pretty far. If I was closer, maybe. Okay, so let's go ahead and move on to this. I thought this was interesting for you guys to look at. So I'm sure you've seen stuff like this, but I guess the interesting thing of note is the direction that this was taken.
Okay.
So in April, I went to Australia to meet with my fiance, and we went to Kangaroo Island, and this was looking directly south. So I'm curious what sort of explanation that you guys might have for this sort of observation. Because obviously, like on the flat Earth, so this is kind of where I was looking out. That's the way that the angle was with the camera, and we see these stars rotating in a clockwise direction around, I think the rotation point's somewhere around here, right around in there. So that's technically, for me, that would be the celestial South Pole. So if you were to, on a globe, to extend the South Pole out and sort of
is the Southern Cross in that picture?
Yes, it is. Yeah, it's right there.
Okay.
Yeah. So the Southern Cross is going around this way.
Yeah, so when you're dealing with the star rotations, first off, just for data's sake, right? Did you happen to have like a compass or any way to verify the direction that you were facing?
Yeah, I had a compass. Yeah.
Okay,
yeah, awesome. because we had to use the maps to drive there and we had to navigate there and everything. So, and we just looked out into the. I mean, if I zoomed into this map, this flat Earth map here, I would be standing on this edge of the island, looking this way. So, yeah.
Sure. I mean, the thing is, when it comes to the stars, there's multiple explanations that we can try to explain what's going on there. None of them in any way actually prove the shape of the Earth one way or the other. That's why, as Dave's famous for quoting, shape of the lights in the sky don't indicate the shape of the floor unless you beg the hell out of the question, as the globe does tend to do. So with the observation, I've actually been challenged with 3 points, right? You have somebody on each continent at the same time looking out apparently south, right? So there's a couple of issues. For one, I do understand that you have a map that you can use to navigate locally. However, when it comes to the larger scale, there's also something called magnetic declination there, when we actually tried to navigate using a globe back in the 1800s, we were wrong consistently. So we went back and we made all these corrections. And I say we, the British military did. So went out and made all these corrections, and now we have our ever fluctuating magnetic declination map that's almost impossible to predict more than a few years out. What predictions we do have are iffy at best, but we're still going to invoke that maybe we'll have a shift in a couple thousand years. This is actually going to determine how we navigate. However, the stars themselves are not going to be oriented based on the magnetic field, right? So how do we actually verify the direction that you're facing, literally like on the ground versus to the sky? Like, how do we know that you're actually facing south in relation to that map to then have to explain the phenomena?
Well, because I could see where we were through GPS, and you can see on the island, because so Kangaroo Island is an island, right? So we have to go out to the island, and it only has certain sides, and we were staying on one side of the island, and so obviously we could see that we were not on the other side, which was toward the north, and we knew that because when we took the ferry over to the island, we came off of a certain part of Australia, the southern out of South Australia near Adelaide, and then we came onto Kangaroo Island, and we went towards to the left, and on either a globe Earth or a flat Earth map, you're still going on to one shore side of.
So long story short, you use GPS, right?
No, because we could see we drove 10 hours from Geelong, Australia in Victoria near Melbourne, all the way over to South Australia.
If the circle was like 5 miles in diameter, you wouldn't even realize that you're making a big circle, right? That's why people get lost in the desert constantly. So I mean, to say that you know definitively the orientation that you are, based on like something like the GPS, or that, oh well, we were just traveling and it didn't feel like we were turning left or right. That's not very definitive, right?
Well, there was no inaccuracies. I mean, there was nothing to say that we were wrong, and we never.
Well, if it was backwards, let's just for a moment, and I know that we're going into conspiracy land, right? We make no bones about it. There's a conspiracy, right? If there was a conspiracy and we're dealing with something that is a projection from reality, I mean, why wouldn't they make it accurate, right? People would figure it out immediately if the maps weren't adding up. But I would add that people actually aren't navigating using a globe Earth, right? They're actually navigating using flat maps. Most commonly, the Mercator projection, 99% of maps are flat. There's only one map that's not, and that's a globe, and it's not even really used for navigation, right? When it was, it failed, and they had to invoke a changing magnetic field.
Okay, but this is kind of hard to discuss, because I feel like it's so like point blank. Like even if the maps were distorted or the GPS got me to the wrong location, I was still on a certain, like I could see the coast. I was on the beaches, and you could see the consistency with that, with satellite imagery, with GPS, with maps, with compass. I mean, it was all, there's nothing wrong with it, I guess.
Joel, so first, when navigators are using compasses, they're in the south. The farther south they are, the more out of sync they are. They find themselves 20, 30 miles a day off, according to their compass. So what NASA has done is they've taken all those data points and they've programmed them into GPS. Anybody can use GPS, but nobody is allowed to see the source code, because if we saw the source code, we'd say, whoa, why are they making all these adjustments? So you have no idea what direction you're facing down there, but let's pretend you are facing south. That we don't even know if the southern stars are a reflection of the northern stars. We don't know what they are. We don't know what stars are. We don't know anything about them, and their motions have nothing to do with the ground that we stand on. Can you admit, if we're on a ball, that there's physical curvature?
Yes.
Okay. Yes. So if I'm on and wherever you are, let's just say it's the top of the ball. Okay. So I'm here on an airplane, and I'm looking at it's a perfectly clear day. I'm on the runway, and I could see stars on the horizon. So I'm looking this way, and I see stars right on the horizon. Right.
Yeah. Right.
So I'm in Germany, and I'm going to fly to Brazil. So I'm flying down over the ball. And when I get down here, those stars that were on the horizon are now over my head, right?
Well, it depends. It depends, like how much the Earth is rotated in that point. But yeah.
Well, the Earth is rotating this way, not this way. So I'm going from the north, right? The stars on the horizon. If I stayed there, and the Earth is rotating, those stars are going to stay there.
That's right.
If I go down, those stars should be on the top. So I want to show you a video that a pilot gave to us, and this is from Germany to Brazil, and it's a time lapse. And if you look at the stars, they're not rising up. You would think that they would rise up, but they're just the only time they move.
Yeah, that's an awesome example of him going along with the Earth's rotation.
No, so this is what Google Earth says that flight should look like, right?
Yeah,
Google Earth says
Google Earth isn't rotating actively.
It doesn't matter. The rotation, the east-west rotation, has nothing to do with north-south navigation. The stars, as he's diving over the Earth, these stars should go up. So this is reality versus Google Earth that is simulating what we're supposed to see on a ball. There's a problem. There's a big problem there. This is what it should be. These stars should just be rising up as you're diving over the ball. Whether it's spinning or not spinning has zero.
Dave,
if you were flying east or west on the equator and you had something on the horizon, yeah, you're flying towards it. It's going to go up or down slower, but north south has nothing to do with the spin of the Earth.
Wait, you said he's going from north to south? Are you saying he's going to north to south in that?
Yep, north
video?
to south. Yep.
Yeah, that's why you see the stars rotating this way.
Where was he flying from?
From Germany to Brazil, I believe, or somewhere. Germany for somewhere down below the equator.
Okay. Trying to think.
And you can think. Here's one. Think about it, and maybe not.
I just think, Dave, that the answer is the Earth's rotation, and so to say that has nothing to do with it, that's just dismissing the main reason that would happen.
Well, let's look at the Earth's rotation. You got a plane here in the north. Let's call that Germany, and they want to fly here. Okay, right? But the Earth is spinning, and by the time he gets here is now over here. So he has a choice. He could kind of keep correcting to the left, and chase it all the way over. Or he could say, you know what? I want to go here, so I'm going to fly this way because by the time I get there, here will be there. Okay? No one ever does that. Airplanes pick their location. They say it's that way, and they head in a straight line and go that way directly to the location. Okay? If the Earth was spinning, you got a problem, right? But the spin of the Earth, you gotta model it out. The spin of the Earth, east and west, have nothing to do with that observation.
Yeah, let me show you guys something. All right, so before you dog on this program, I need to tell you that it's extremely reliable because I've used it most nights.
Goes off of azimuth measurements.
Well, no, it does have an azimuthal grid, but no, it doesn't just purely go off of azimuthal. So this is close to where I was in Australia, so you can kind of see the same thing that was in the video.
Was the ground curved like that where you were? Did it swoop up?
No,
like that?
Obviously, like if you zoom out all the way, like it's going to be, it's just a matter of point of view. So really, it was probably closer to something like this. Because it was a wide angle lens, but otherwise, the reason I had to do that because otherwise you couldn't see enough of the screen. But the point is, this is looking directly south. That's right towards the South Pole, and I want you guys to notice the specific stars that we have here. We have the LMC, which is the Large Magellanic Cloud. We have the SMC, the Small Magellanic Cloud, and in terms of the Milky Way, you have the core there, and then up here you've got where's Polaris? There's Polaris. There's a crux.
So we're not even. Okay. But we're not even really looking at the sky here.
No, but if you went to the same location and looked up, this is exactly what you would see. So this is a reliable software program or software.
So let me just before you finish that point, if I put you in a planetarium and it showed you those same stars in the same locations, would that mean anything?
Well,
would that mean the Earth is a globe?
Well, so sort of, because
so the planetarium proves the Earth is a globe because you're on a
No, no,
floor
no,
in a
no, no, no,
planetarium.
no, no,
You're
no,
looking
no.
at lights in the sky that are
Dave,
50 feet away from you, and you think that
Dave,
they're trillions
Dave,
of light years. Go ahead.
Dave, I need you to be charitable with me here a little bit because
Go ahead.
what I'm saying is if what you see in the planetarium is the exact same thing as what you see in real life, then it's reliable. It's not just because you see it in the planetarium. Okay, this is just what I can use because obviously I can't take you guys outside to look up. But this is so in the southern hemisphere we have that's the southern celestial pole right there. So all the stars, you're on the bottom of the globe in Australia, and you're looking down towards towards the downwards from the Earth, from a right side up Earth anyway. And then here we have where I am. And you can see totally different stars. You could see, so this is the literal opposite side of the Milky Way because the other part was down here. You were looking through there. So this is what I see every night where I live. And they're actually rotating counterclockwise around a different point. These are different. You didn't see Cassiopeia. You don't see M31. You don't see the Big Dipper. You don't see Ursa Minor. You don't see any of these. And this is looking directly north, right? Because that's the North Star. And all of the stars rotate around the North Star. So you have the southern hemisphere where it rotates counterclockwise. And we have all of these constellations. They're beautiful and whatnot. I'm sure we could all agree with that. But they're totally different stars than are over here. Totally different.
So if I may,
different directions.
Explain that with a phenomena that's not the Earth actually curving, right? And just to narrow it down, right?
Well, that's the point. Yeah.
Of course, Joel. Your claim right now is that the way that the stars are moving, right, and the way that they appear to be curving around the Earth, right, is evidence of the Earth curving, basically.
Not the Earth. It's evidence because if you were on a globe and you were looking out from that globe, you would expect to see certain things. So if if you're on the North Pole, you look straight up, you could see the stars rotating directly above you, and you wouldn't be able to see the southern hemisphere. And so, when I took the flight down, I went from Dallas, Texas, down to Melbourne straight, and I got footage of a night lapse of the stars like moving, similar to how that pilot did, except I was looking out the side of the airplane, and I can see the stars literally shifting orientation in the sky as I was crossing the equator and stuff.
Okay, so let me simplify it even further. Then, in your worldview, is perspective an actual thing? Like, do things get displaced in relation to the viewer based on how far they are in their relative position, right? So, in other words, even if we're dealing with a flat plane, right? If something is moving level parallel overhead optically to the observer, would it not appear to drop? Or would it still appear to drop because of perspective?
Like in terms of something getting further away from you, that's like has a certain height, and the further away you get, sort of like looks like it's
two parallel planes.
Yeah. You can see that with train tracks, sure. Yeah, the distance.
So what if the stars were close and local, and you're flying underneath a low sky? You would see the stars curving over you as you go by. They would drop down lower. They'd be high above the plane as you're flying, right? And the reason that you see different stars is simply because the stars are so close. If you and I were in a room with 10-foot high ceilings and there's recessed lighting and they're in all different patterns. Look, there's a starfish and there's a bull and there's a cow. And I say, hey, Joel, walk 5 miles. We're going to expand the room to 10 miles wide. You go 5 miles down, walk there. So I wait, a little while, and I can't see you anymore because my vision has brought the ceiling to the floor and you are too small for me to see. So I call it and I yell and my voice spreads out like light spreads out and you can't hear me. So I call you on your cell phone and I say, Joel, are there still lights above your head? You'd be like, yeah, I see a horse and a dog. And I'm like, well, what happened to the cow and the bull? Well, I can't see those. Okay. You can't see the stars that I'm under. I can't see the stars that you're under. And we're just 5 miles apart with in a small room with no atmosphere causing issues, just perspective. So that's why you can't see the same stars from the south because they're too far away. Problem is, on a globe Earth, there's a physical horizon. So on a globe Earth, if you use globe math, you love math. There's a certain distance, which is the max distance you can see. Never, ever can you see farther. Only if conditions like waves on the water or density of the air could you see less. You can never see farther because there's a physical horizon. On a flat Earth, our horizon is very optical. And depending on weather conditions, we can see farther than we should be able to see. So, a 6 foot tall person standing at the edge of perfectly calm water on a perfectly calm day, a perfectly clear day, should only be able to see the surface of the water for 3 miles, according to your math. Okay, there's a 6 foot drop in 3 miles, according to the Pythagorean theorem. Okay, so I shouldn't be able to see the surface of the water, but we can see the surface of the water for magnitudes farther than that. We can see things magnitudes farther, right? But globers like to say, well, I can't see that mountain. I can't see that mountain, therefore the Earth is a globe. And then we break out a infrared lens, and all of a sudden we're like, oh, we can see that mountain with infrared. And infrared, and the only thing they have is screaming refraction, but infrared even cuts down refraction, right? Without an infrared, you see a blue sky, right? But we can see this mountain with infrared. And infrared, if it's refracted up, it should be even less, but we can see all of this mountain except the lower part because the atmospheric density. So we can see too far because the horizon is a theoretical limit of your vision. Okay? It's not a physical horizon.
Yeah, but what about the rotation? Because that's specifically the
What the rotation?
So
the rotation of
so the rotation is a so this is something that I've actually been trying to send you something, Dave, for the background because I can't share my screen while I'm streaming. Otherwise, I'd pull up the visual for you. But we actually
where are you sending it?
Well, no, it's just too big to send. So I was trying to send it in my email, but it wasn't working. But anyway, in any case, Walter Bislin actually did us a favor on this and actually modeled out what the stars would kind of look like on a flat plane. They did use arbitrary stars, so it's not like you can see specific constellations or anything like that, but it basically just shows the general position of where the stars were and then what it appears to be optically to the observer. The reason why this happens is there's a huge discrepancy or a miscommunication in what we're actually dealing with. So we're dealing with measurements in our visual field. Right, we're dealing with things that are very far away, and there's a big assumption that everything is in Euclidean geometry. We assume this because for a lot of things it tends to work. But if you Google it right now and you look up the geometry for visual space, you'll actually see that there's not a set model for it. So, oh, good. They've got it pulled up right there. Perfect. So there's actually not a set model for what the geometry we should expect to see in visual space is. And there is now evidence coming out that we are seeing a hyperbolic geometry as our visual space. So in other words, spherical geometry. There's something known as the Alley experiment. There's a paper that is referenced that I also sent Dave a quote from. Then this would explain the spherical nature of what we're seeing. As far as the rotation goes, it's an optical phenomena. So it's literally an optical phenomena. You would have an optical convergence point at the furthest point away from the center point of rotation. Because again, the further out that things get, the more they're going to tend to converge. So the things that are rotating above you are obviously going to, if you're over the equator, actually, it's going to appear more straight. And then as you get further away, it's going to optically converge again as you look out. So this is just one of the explanations. Another explanation is that there's literally 4 different optical rotations, which is very possible if you just think of it as like gears, right? You have one rotation in the center and then 4 opposite parts of rotation coming off of that. So, but before I even attempt to explain any of that and get into the bottom of what's happening, I like to start with first principles, which is why I had asked you, how do we even verify the general position of where we're looking definitively, right? There's the quote right there. Euclidean geometry widely accepted as the model for our physical space. However, there's not a consistent model. There is evidence that our eyes work to make pictures and images of the physical space using a hyperbolic model. And this is obviously what we're basing our measurements off of. So I'm wondering what you would say to that. And if this is true, where is this accounted for in the mathematics that you present?
Well, there was a lot there. I got some stuff down. It certainly wasn't any simple sort of message that you just gave there. So you're talking about non-Euclidean geometry,
Right.
okay, and how that relates to our sort of more hyperbolic perception. But but you mentioned how, so for example, if you're on the equator and you're on a globe, you would expect the sort of the stars in the sky to sort of barrel over from you have the north here, the south here, they barrel over you just the same way. If you turn it right side up and you're on the North Pole, the stars would just rotate around that top point. If you're in the South Pole in Antarctica, you look up, it would be the same thing, but with different stars. So, but my question is, with what about the different stars? I mean, they're completely different, and you can watch as you traverse the globe, the
Joel.
different stars as
So
you.
that's actually so that issue was actually solved before the rotation issue was even solved, right? So what happens is, because our visual space is curved, the things that are further away are obviously going to be dipping down. So what ends up happening is these stars, the stars that are over, let's say, the northern hemisphere, as you drift over the equator, you're going to start to see both of them, because again, the closer you get to something, the more it's going to rise up to your perspective. The further away, the more something's going to fall. So as you move away from the northern hemisphere, those stars are going to fall to the horizon and become invisible to you. And then the stars that were invisible to you, that you moved closer to, are now going to be visible to you. Long story short, let's pretend you're in a big warehouse with lights over top. You're simply underneath one set of lights.
Yeah. You're 5 miles away in the same room. We look up, we see the different stars. Now, as you walk towards me, you can't see the stars that you left behind, and you start to see the stars that I'm seeing. You're on the north side of the room, on the south side of the room. Okay. So it's the same thing. What's that?
How low are these stars to be?
We don't know. We don't claim. But, I know how low they're 25 trillion miles away. I just made that up, right? But your theoretical ideas of where the stars are scientifically impossible, if you ask me. Our stars are very close. I don't know how far they are, but I don't think they're thousands of miles away or millions of miles away. I don't know. I'm not going to make a claim. Well, I like looking at things here on Earth that we can actually measure.
This is just a question. I'm saying, so if you were to measure and work out the math of how far something would have to be to go a certain distance away from it to where it looks like it goes down.
Well, here's the problem.
You've seen mathematically.
Well, you've seen the orthographic view of like, the flat earthers say the sun's 3,000 miles up, and with the size that they say the Earth is, the sun would never set. Well, I don't think it's 3,000 miles up, but even if it was, they're not taking into effect that somebody standing under it, it's directly above them at X height. And now somebody farther away, it doesn't stay at X height. It gets lower already just due to perspective. And then they go farther away, it appears lower and lower. Okay. Phuket Ward, you don't know who he is, but he recently did a video on it. And it's really, it's how perspective works. People, they don't teach perspective in school, because if they did, people would be like, wait a minute, this doesn't work out. We don't live on a crazy globe. I want to get back to, you're talking about seeing the stars and stuff. The stars, we can't prove what they are. We don't know what gases they are. We don't know how far they are. The brightness is 2,500 times brighter than the sun. That's a made up story.
Well, that's only one star, though. There's different ones that have different.
If you told me something was 1.5 times as bright as the sun, I'd have a hard time believing it. Okay, because the sun, because no, you have no examples of anything brighter than the sun. Let's say, they could do something in a lab, and they say it's 10,000 times brighter than the sun. Show me something twice as bright as the sun. They've never ever done it. But instead of looking up at these lights in the sky, let's just come back down to Earth for a minute. You said earlier, you agree there's a physical horizon. You agree that there is curvature of the Earth. Do you know anyone in history, or have you ever measured the curve of the Earth?
To the second question, no. To the first, I would say yes. But
like who? Well, and the other one is axial rotation. Do you know anyone in history that measured axial rotation? And can you tell me how?
Axial rotation? What do you mean by that? Like
the Earth spinning on an axis. The Earth spins on an axis.
What do you mean measure that?
How do you prove the Earth is spinning, but without looking at the lights in the sky?
what do you think would be a satisfactory answer for you, I
The Earth
guess, for
isn't
that?
spinning.
No, no, no.
I,
I meant to test it. If we were to have a test of that it's
if the
rotating,
Earth
what
was
would that look like?
spinning or curved, you'd be able to measure curvature. So let's look at
Oh,
this. Okay. So when you're down low, that thickest part of the atmosphere, you can't see 100 miles. Okay, because the atmosphere just becomes too thick. Right. But the higher up you are, the air is thinner, clear, less pollution, less moisture, and you can see farther. Here's an observation from a mountaintop.
Oh, yeah, I watched that video. Yeah,
You watched it. So,
yeah.
what is your explanation on why we can see these mountains? We can see all of them in the right places and everything. The tops of these mountains should be over 40 miles below the curve. Now, you can say, well, the curvature calculator is wrong. It's a parabola. You can say whatever you want. Oh, it's the hump. It's the Sagitta. Okay, only 20 miles. The tops of these mountains, which is nonsense, should be 20 miles below the curve, but we can see them. What is your answer for that other than refraction?
I'd have to look into that. I can't just like give
You know
a.
what? You would be the first one with a scientific belief system that is willing to look in it because mainstream science won't look into it. No one will look into it. Okay.
Yeah, I mean, I could look. We got that down for next time then.
There you go. Come up with an explanation on how we can see all of these mountaintops.
Okay. Yeah, yeah, I will.
All right. Beautiful.
I
Um,
like how you assume on faith that the curvature calculations are just going to work out. It's all going to work out. Those
I
mountains
never
are
said
fine.
I'm good. Okay, okay, but Skylar, you've got to like give me. I mean, how would you work it out then? I guess like
Well, there's an Earth
what
curvature
method would you
calculator,
use?
right? So I would simply find the height of the mountains, right? I'd get the distance of the observer here, 700 miles, the height, and then I would plug those numbers into probably the Walter Bislin Earth curvature calculator, and then I would invoke standard refraction just to be a good sport, right? And then yeah, I would see what figures it give me, and then I would compare it. When you do compare it, it says that there's like 80 miles of curvature that's supposed to be there. Those mountains are not 80 miles high. So that these are the things that to us, seem to falsify the model that everybody just keeps insisting on with hypothetical, celestial proof.
Well, I think celestial is strong because again, if we are on a globe in space, you should be able to look away from it and be able to be able to predict what you would see. I
But the
guess is what I'm saying.
but the whole thing with so the assumption of Euclidean geometry being shattered doesn't shift or make you want to relook into
It's
the way that
not.
we're
I
doing
don't think
these
it's shattered. I
calculations.
mean, obviously they just said there's alternatives and there's different like ways to mathematic like the difference between radial
No, well, so
like
when I say
radians and
shattered, right? I mean, I don't know how it could get more shattered than well, they nicely did it, right? They said the assumption of Euclidean space is wrong, and we have evidence that we are building our space in hyperbolic geometry. So I'm not sure how we wouldn't consider that shattered.
I actually think that's actually referring to like math, like tensor calculus, and like general relativity, because that's using Euclidean geometry, and they were sort of criticizing.
So this all was done as a result of the alley experiments, were terrestrial experiments, right? So we're not dealing when they did this observation, they weren't even using celestial observations, right? So this can
Oh,
happen
okay.
in the small scale, which is again, this is the kind of stuff that we like to go on when you say that, well, yeah, both sides are taking something on faith. Kind of, at least our side, we have the ability to go and verify the terrestrial examples, whereas your side, we have to take on faith that this entity, NASA, started by Project Paperclip, Nazis, admittedly, sent probes out and gave us back the correct data.
Yeah, I mean, but I guess, because then I just ask like, and then like, what is this thing? What is this? And then what are
Well,
these?
well, could you accept that
What?
we don't know, and that maybe the people claiming to know are just trying to get a leg up of credibility? Or that maybe
Well,
you've been misled information wise, and that the people who are actually doing the work on the ground don't claim to know these things, right? They claim that this is a theory that could explain the phenomena, but it's a work in progress, and it's surface level at best, right? It doesn't even begin to explain the deeper phenomena. Like you can't explain what
but
gravity is, you can't
but we
explain
can
quantum
we can
mechanics.
We can see other galaxies, though, is what I'm
Joel,
saying.
you see lights in the sky that somebody told you is another
No, no,
galaxy.
no, no, no. Well, you could see the shape. Like you can
You
see
can see a
the
shape that
galaxy
somebody
itself.
told you is another. Like, did you take that picture behind you?
Uh,
Where's that
yeah,
picture from?
yeah, I got it. Yes, I took this picture
You took that with your camera.
with my GoPro. Yeah, right here.
Your GoPro took that picture of the sky.
Yes,
That's a good picture. Good job.
thank you.
You're taking pictures of lights in the sky that are not hundreds of trillions of miles away. They're close. They're close. But to assume that, oh, that's a disk shape and it's kind of fuzzy, therefore it's 100 billion stars with a trillion planets, right? To believe that's just a belief, right? So here's the example I'm looking for. Okay. Is this the sun or the moon?
I can't tell. Probably the moon.
Is it a sphere? Is it a sphere?
I also can't tell.
Okay, that's right. And guess what? It's only about a quarter of a mile away. And as we bring it closer, you see that it's a train and it's not even a sphere. Okay, it's got rectangular lights on it, right? It's got orange lights, it's got different color lights, but you saw a sphere at a quarter of a mile away. But you think that you can see a light in the sky 100 trillion light years away and tell me what it is? You couldn't even tell that this is a train with 8 different colored lights of different shapes that are not even touching each other. It looks like a sphere. It's how we see.
But what about things that are shaped like what we call galaxies?
They're
Spiralites.
shaped like what we call, an egg is shaped like a galaxy. I don't think there's 100 trillion stars in my fried egg in the morning. Okay. It's shaped like a galaxy. It should be. It should have 100 trillion stars in it, and it should be amazing. I bet if I took a really close up picture of it, I could send it to NASA, and they'd be like, "Wow, you discovered a new galaxy."
Yeah. Oh, I mean, okay. Just I don't
Thank you.
know.
I'll take an okay. I'll take an okay. That's all you need. That's all you need to give me.
Yeah. I just I wouldn't really know how to respond to that. Just
But here, I think I made a good point. You couldn't tell what shape this was, what it was, or anything at a quarter of a mile away. You think that you can tell what something that looks like? They say, "Hey, a galaxy is this shape." Okay, you think that you can tell what that is? You were told what it is, and therefore anything that's that shape, you believe it because that's what you were told. There's zero evidence for anything that you have brought up today. It is all theoretical. And getting back to the spectroscopy experiment, I want someone to do a I can't say the word, spectroscopy experiment. You get a vial. We should be able to get a beaker full of whatever gas, put a bright light behind it, set it on fire, whatever you want, and somebody a quarter of a mile away we should be able to tell them what it is.
That's not how spectroscopy works, though. That's not.
How does it work? we already went over this. We
already went over that. But
okay,
so let me just one more example, and then we can start
go for it.
Shutting it off. But so this is the same program. I've seen these things myself, so I'm not like just showing you gibberish that I haven't seen myself. First of all, I'm sure you've heard the Andromeda Galaxy. That's our nearest galaxy. It's quite large. It's huge. I've seen it. You can see the shape with a dark enough night
right now.
What's that?
I said I can make that in Canva right now.
Yeah, but I'm not. You can't say this is fake, Skylar. This is real. I've seen it. This isn't like some made up. We have pictures of. You can go outside with a telescope right now with a DSLR camera, put a star tracker on this, and take a picture of it. So this isn't like some just made up thing.
You said that we could put a star
light
tracker
in the sky.
How is it that we're keeping up with this other galaxy, right? That's definitely not within our galaxy. When we're whipping through space over 1 million miles per second.
Well, because space is really big. So here's another one. So here's the Whirlpool Galaxy. I've seen this one too. You can see the shape. You can see the smaller galaxy here. It looks like it's kind of sucking it in. It's really cool. And then here's another one that I've seen, the Triangulum Galaxy.
Skylar, what if there was a book that said that these are spiraling lights that were just a couple hundred miles away? And that's what you were taught. Now, if I showed you all these and told you that there were galaxies trillions of miles away with hundreds of billions of stars that are bigger than. But my point is, you could defend either one of them with an equal amount of evidence, which is zero.
I'm saying so.
Try not to do a spit take.
It's sort of like what you're calling it. It's just a matter of it's like semantics of what you want to say that it is. And then, of course,
We're
this would
looking.
be our galaxy that we're inside of, so we're inside, that's the center of it, and you can kind of look away from it. So this is our Milky Way, obviously, and any of us could see that.
It's not obvious because you were told that. You're
No,
pre-assuming.
no,
I
no,
call
no,
it the
no.
Great
I'm
Rift.
saying that this is all stuff that you can go out and see yourself, and that you can
You
take
could,
pictures
but
of.
but you couldn't tell what a train light was, right? It's a cool story, bro. It's a cool story. So you have zero proof of it. You were told that it's a galaxy. You were told that it's trillions of miles away. You were told it's 2,000, or you figured out on your own that it has to be 2,500 times brighter than the sun. These are all things that you have zero evidence of. Zero.
But wouldn't the evidence be the observation, like looking at it
The
and seeing
observation,
what
So
it
but
is?
here's why
as I
it's
said
not.
before, if you were taught in school that these galaxies were actually energetic sources of spiraling light that are a couple hundred miles away, that would be your story.
Well, hey,
And
you
then
know what? There
there's
was
another one.
actually
There's another
you
one.
can
There's
look it
another one.
up. There was something, the one of the biggest debates in astronomy was actually this exact point, when we believed that the Milky Way was the entire universe, and we didn't believe there was other galaxies. We didn't even know what a galaxy was, and so where'd he go?
I'm
We
still
good?
here.
I'm
I'll be
here.
right back.
Okay. So the point was it was called the Great Debate. You can look it up. Where it was Andromeda, that first one that I showed you. They were saying, "Oh, that's actually not a nebula." They thought it was a nebula, and turns out, well, Hubble discovered that it was a galaxy, and you can look up how he did that. But
So they changed their story. They literally just changed their story.
well, I think it would better term would be updated their story, but.
Well,
So
that would be
so
impossible to catch them in any kind of like.
right.
How can you falsify the model if you're just going to change it whenever you get narrowed down?
It
on
wasn't.
something?
It wasn't falsified. It was added because they didn't deny that the Milky Way was existed. They just said,
Kind of like
"Oh,
refraction.
actually,
Kind of like refraction was added to save Earth curvature.
well, you and I both know that refraction is a thing. Like you can see how refraction works. You
So
can
No,
test
refraction-
that.
refraction never brings anything up that's gone. It can move things that are in your visual range, but it doesn't bring things back from when they're completely hidden and keep them there over 24 hours.
I'm just
changing weather
saying
conditions.
refraction itself is a thing.
Refraction, but that doesn't explain the observations. For example, the famous shot across Lake Michigan of Chicago. There's a time lapse, 24 hours with different weather coming through day and night, and the buildings never move 1 inch. They're just there the whole time. And we proved that they're not refraction because a couple of our guys got in a boat and watched it and went across the lake, and it should have disappeared at one point because they're getting closer to it. The refraction should change, and it never changed. We proved that it's not refraction.
But all I'm saying is, with the Great Debate, it wasn't falsified and like debunked. It was just added onto. They're like, oh, I guess the universe is way bigger than we thought it was.
Well, that's again theoretical nonsense. You believe that this is a giant star manufacturing factory where there's dust and gas in space, another scientific impossibility, that is collapsing upon itself and spitting out stars like ping pong balls. Okay, that's what you believe, right? This is a nebula that produces stars.
Yeah, that's the pillars of creation. Yeah.
Yeah. So cool story, bro. It's a cool story. It's not even a cool story. It's ridiculous. Okay, how do you have gas and dust in space?
Well, I think we probably won't get into that topic here, but
God,
When you say things like,
God.
my issue is when you say things like, well, the observations are the evidence, right? Do you know that we changed the distance to the sun like over 7 times in modern history?
yeah, probably.
Okay.
We updated it. I think we got more refined.
Do you know why that's
Yeah.
significant? Do you know how much they
Why?
changed it by first off? Like, do you know how much they changed it from?
No.
1,000 miles was the first predicted distance. So they have
who did that?
I can't remember the exact names of everybody who did the predictions, but in any
Okay.
case, we end up now obviously with our figure of 93 million miles. You admitted yourself that well, yeah, they probably changed it to update it, right? So here's the issue. We base a very important unit of measuring all these other distances off of our perceived distance to the sun, which was the astronomical unit. It's also how we defined our speed of light, right? We simply define it as constant. We think that the sun is so far, and then we measure differences in angle. So it's pretty funny that we don't actually have in my opinion, a real measurement, a direct measurement of light. It's an inferred measurement. But in any case, the AU was changed 7 times, which means that the units to all the other stars were changed several times. And now, I mean, this point was kind of breezed over when Dave brought it up. The North Star, they're talking about give or take, right? That means they could give it 100 million or 100 more
light years.
Yeah, 100 more light years, or take 100 light years away. That's a 200 light year discrepancy. And we're going to sit here and pretend that that's not going to have anything to do with the other predicted distances, when we know that several other predictions were made about the distances to other galaxies and other stars based on where our projected distance of the North Star was. It's a house of cards.
Joel, the mainstream science, if you don't agree with them, you don't get published. So mainstream science tells us it's 93 million miles away. But during one of the recent solar eclipses, a bunch of truthful, honest, researching amateur astronomers said, "Hey, they did the math, and there's something wrong. The eclipse doesn't work. The sun has to be farther." And I forget the number, but it was significantly farther. And so all of these chat groups, these articles started popping up, and then they all disappeared. Inside of a couple of days, bam, you can't find any of them. It was completely squashed off the internet. And wait a minute. There's something wrong with the eclipse and the shadows and everything. It didn't line up. And that was just squashed, and nobody heard about it.
That's interesting.
It is interesting.
Yeah.
So I got an okay and an interesting.
Would you be able to acknowledge that, again, this is why I say it's theoretical at best. I'm not saying that the theory can't work, right? It very well could, but we can acknowledge that the observations on their face are not proof of themselves. In fact, you even stating that is a literal begging the question, or also known as a reification logical fallacy. If an argument is logically fallacious, then that means it's not good support for that claim. Not necessarily that your claim is wrong, but just that argument is not a good argument for that claim. So when all of your arguments pretty much are like that, it's flat earth or fuel.
No, I don't think all of my arguments have been like that. Not all of them, but yeah, it is a. What'd you say the specific name of that fallacy was?
Reification.
Reification. Yeah. So yeah, I mean, it's hard. It's. I could scrub through this whole video and watch it back, and I'm sure all three of us has made plenty of logical fallacies in the stuff we said. So it's kind of really, really hard to avoid. But yes, and to your point, it doesn't necessarily make it valid. So I guess it is a sort of pleading the question or begging the question. But I guess that if I acknowledge that, I also like if you guys could maybe acknowledge that if on a globe model, those celestial movements would make sense if it was a globe.
Which one specifically?
The rotation, the celestial rotation.
Sure.
It would make sense on a globe.
Yeah, I'd give you that. Okay.
Yeah. All right. Well, I think this was productive. It was very involved, very in depth.
There was a third question I wanted to ask you. The one was axial rotation. No one's ever measured it. The curvature, no one's ever measured it. And high pressure next to no pressure. Have you ever seen or heard of a test in a lab or in nature that can have high pressure next to low pressure without a physical barrier in any orientation?
Hold on. Is the question high? So the question's high pressure next to low pressure.
Yeah, without a physical barrier.
Hold on. Let me see. I'll write this one down too. I mean, but the thing is, when you start talking about these things, you have to start using things like Boyle's law and fluid mechanics and all this stuff that is mathematical, so it's hard because when I sort of like start responding,
I don't look at it that way. Math is not empirical evidence.
Well, yeah, but when you're talking about these concepts, the way that we understand how things interact, how things
So
high pressure and low pressure, why it goes.
here's an experiment you can do.
Pressure.
Get a cube, a box that you can suck all the air out of, right? And carry it around with you. Let's say it has a little trap door that can be opened on the side, on the top, on the or the bottom, right? Is there any place, any altitude, any place in this world where you could open that and it wouldn't equalize instantly?
Not that I'm aware of.
So how do we have a high pressure atmosphere next to space, which is no pressure, not even low pressure, no pressure, like insane?
Well,
right?
you know my answer to that.
Gravity, right? So you've seen the train car that they suck the air out of and it collapses upon itself,
yes.
right?
Yeah.
How come?
I think we've all seen those videos now.
If you did it the other way, you agree it would explode, right?
Yes, yeah.
So how do we have spacecrafts made out of aluminum? How's the ISS up there, which has high pressure in a no pressure, not even low pressure? How come it doesn't explode? Because the vacuum chamber we have here on Earth has walls 10 feet thick out of steel and concrete.
David, the hard part is because then you have to start quantifying, okay, how much pressure is in here, how much pressure is out here. So you start getting numbers, and then you have to start using mathematical relationships to describe why something would or would not
Forget
happen.
that. Show me in reality.
So that's what I'm saying, Dave.
Listen,
I'm saying
Google Earth.
Hard.
Google Earth showed you using math how the stars should rotate. Reality shows you something else. That pilot didn't use any numbers. He filmed reality, but Google Earth used mathematical equations and numbers and everything, and it worked perfectly for a globe. But reality. So show me in reality. Don't show me in Narnia math, right? Show me in reality. Take a box of vacuum, find a place where you can open up in any orientation that little window, and it won't equalize. And the answer is you can't. Nowhere. Not in Death Valley, not at the top of Mount Everest. Nowhere. It'll equalize instantly. That shows you that we are not on a globe. We're not on a globe. I don't believe space is a vacuum.
But
okay?
So if I was to show you what pressure was in a spacecraft, for example, and how maybe it wouldn't overcome the structural integrity of the outside of it.
Let me interrupt. All right, go on YouTube and search vacuum chamber. Okay, they explode. Anything you put in there explodes. When they put a soda in there, it explodes. Okay, when you open up a soda can, it equalizes instantly. Right? Get a vacuum chamber and put something in it and suck the air out. It's going to explode. Okay, it's going to explode. Right? But the space station, no problem. That their seals work perfectly. Everything works years and years and years. They run around in gorilla suits up there. They got a meteorite, a mini meteorite, put a little hole in it, and they fixed it with duct tape and gum. Okay? They're mocking us, Joel, and you're buying into all of it. Okay? Listen, you are a super book smart guy. You're a nice guy. You're super book smart, but your book is Narnia. You're literally living in Narnia.
I'm not sure how I could respond to that.
Because you know what? Narnia is kind of a nice place. It's kind of fun there, I heard.
Yeah, I would agree. But
I wouldn't know though.
No, of course not.
Well, what do you make of the? I mean, I know it's one thing to say that we just disagree with your beliefs, right? I mean, that's one thing. But what about when you have the people, I won't even call them the so-called elite, but like some of the people who have come out with some of these theories, like Kepler, saying that we need to, or sorry, was it Kepler or Hubble that said that we must avoid the unique position in the universe at all costs. Such a position is unwelcomed and would only be accepted as a last result, as a last-ditch effort to explain a phenomenon. In other words, what he's saying is we will make up anything, literally anything, including magic bendy light, in order to save a model that will mean that we can explain away some certain observations. Observations, of course, that we're not moving, that we're at the center. And believe it or not, observations that we are, in fact, not curving. Again, those would be radar. We have radar propagation over 10,000 miles, and it apparently operates in the manual off a line of sight, meaning you point and shoot where you think the target would be. There's no calculation for bouncing it off of the ionosphere. And we even have radio waves that go over the 100 megahertz broadband, which means it goes through the ionosphere. We have clocked those at over 2,500 miles. These observations alone, by themselves, destroy the curvature claimed by the globe. And so we don't have good evidence of its curving. We have evidence that it's flat. We have no, as you even admitted, no evidence for the celestial model that doesn't beg the question. So there's no.
When did I admit that? Oh, that doesn't beg the question.
Right. Reify. That's why you don't know how to answer when we accuse you of living in Narnia, right?
Yeah, right. But that you just, I granted it to you when you just said that, because you said we have observations of this stuff happening.
Right.
So you were you doing the same thing, but I gave you that because, you can't always avoid that. It's a very particular fallacy that's one of the hardest to avoid, besides like the fallacy or something like that. But, So
sure.
you said the same. I need to say that you made the same claim. We have these observations as evidence for the flat Earth, and that's kind of almost exactly what I was saying.
But the difference would be between, and I could give it to you that that's a reification, right? Because just because it shoots as if it's flat doesn't necessarily mean that it's flat, right? It just can hint at that, right? So I would give you that. Yeah. But the difference between our observations would be, again, that we can recreate ours here on the ground. The things that prove out your observations demonstrably are probes, NASA, again, and everything that relies on the accused or reifies the issue.
Well, what about astrophotographers, like amateur astrophotographers?
They take pictures of the sky. What about them?
Well, I mean, because they use a lot of these theories and methods, and they use these star trackers, and they use...
So what they use... So the only thing that you need to know in order to be an astrophotographer really is the cycles, obviously, of the celestial bodies. But then also you just need to know how much they move in a day, which is about 1 degree per hour. So, I mean, as long as you know that, I mean, you don't have to do advanced these calculations, this assumption, right, that you have to know the layout of the cosmos as NASA and the mainstream presents it in order to take pictures of the things up there it's actually ridiculous when you look into it. It's not even claimed that that's the case.
Joel, what happens when you go back and you decide to look at that mountain, that 700-mile mountain thing, and you can't come up with an explanation that works on the globe? What would you do? What are you going to do then?
Well, that's hard because it's very hard for me to just not accept no explanation. So I mean, I feel like I would keep trying. And
here's the thing: that observation, although it's not easy for anybody, but anybody could go there and do it themselves, right? It's not we don't have to go to space.
You could do everything I showed you yourself too.
No, you can't. You're looking at things that you can't tell. Right. If I didn't move that train forward, you can do all sorts of measurements, and you could say that light was 250,000 miles away when it was only a quarter of a mile away. And you could say it's spherical, but when it wasn't spherical, you can say anything. That's not, this is something we're viewing, a terrestrial object that we know where it is. We know how high it is. We can go measure it from another terrestrial place. We're not looking into Narnia. You're looking at Narnia.
Well, things like Jupiter's moons, for example, like you can watch.
Can I call them the light that we call Jupiter, the little lights that are near it?
Yes, I know, okay. Dave, but we're trying to be charitable to each other's positions here. So you can. Jupiter rotates once every 90 minutes, which is insane to me. But you could watch it rotate. I mean, it's such a big planet, but it's rotating so quickly, and you could watch its moons in a telescope rotating around the planet through the night.
I'm with you.
Yeah.
I'm with you.
So things like that.
Ask you a question. Jupiter, what's Jupiter made out of?
Yes.
Spectroscopy should tell you. It's made out of helium and hydrogen.
Not necessarily, because it's not emitting light. It's a failed star.
So what basically. But it's not, it's like 98% hydrogen and helium, I heard.
Yeah, well,
is that right?
I don't know.
Spectroscopy should tell us it's right here. We're not looking at it. It's not trillions of light years away, or millions of miles and millions of light years. It's right here. So the spectroscope. I'm trying to say both words at the same time. It should be able to tell us what Jupiter is. It should be able to tell us what Jupiter is. Okay. So mainstream science says that it's correct me if I'm wrong, Skylar, it's helium and hydrogen. Is that right? Am I right on that?
That sounds right. Yeah.
I don't remember.
So helium and hydrogen kind of defy gravity here on Earth. They also tell us that Jupiter has more gravity than all of the other planets combined. How much helium and hydrogen does it take to create more gravity than all of the planets combined?
A lot. Quite a bit.
And so more of something that's lighter than air. It doesn't make any sense. And then if you were on Jupiter,
it's lighter than oxygen and nitrogen. But yeah,
how NASA says that from Jupiter the sun would be very small. It would be like a quarter of the size. It'd be like a large star.
Sure. Yeah.
Okay. So you have to believe if you're on Jupiter and it's a gassy surface, I wouldn't call that very reflective. I'd call it kind of light absorbing surface. And the sun is really small and it's far away. You have to believe that far away sun is lighting up the gases, reflecting off of them back to us. And it wasn't yesterday, but the last time I saw Jupiter in the sky, it's the brightest thing in the sky next to the moon. Okay. Yeah. So how is that light getting intensified, reflecting off of that non-reflective surface, traveling millions of miles back to my eye, not getting any dimmer, getting brighter? How is that possible? How come when I look at a rock on the ground at noon that's much closer to the sun and much more reflective than a gassy ball, how come it's not shining bright in my eyes? Because I'm right next to it. Okay. It's not as bright. When you look at Jupiter in the sky, it's as bright as the sun. It's just smaller. It's a light. It's as bright as the sun. It's just smaller. Right. But I should be able to look at a rock on the ground and it should be brighter than Jupiter, but it's not. It's not.
Make God great again says Flurfers just don't know how time traveling eyesight works. Obviously, Dave, we probably should just pack it up, call it a day.
Okay.
I'm just kidding.
I don't understand. Like, it's not getting brighter.
Let me ask you a question.
It's just reflecting the light off of.
Is the light reflecting off of this blinding you right now?
No, it's not the sun reflecting off of it.
Should. Now, if the sun was
unless
over
you're
there,
outside, yeah.
If I was outside and the sun was over there, it would still just look like this. And this is actually I'm pretty fucking bright in here. Okay. The sun reflecting off of this, you can just see it. It's not a light. You look up at Jupiter, it's a light, right? But you have to believe that a distant sun, a smaller sun, is reflecting off of a non-reflective surface, traveling millions of miles to my eye through my atmosphere, and I could see it as bright as the sun. I'm sorry, you're not thinking if you're believing that's what that is. The only reason that you're defending it is because it has to be that way, because that's the way it is.
Well, I just don't think that position that you're describing is accurate. Because
all right, explain to me how we see Jupiter as bright as the sun. Well, it's a bright light in the sky. It's bright light in the sky.
It's not nearly as bright as the sun.
Okay, but it's brighter than any star. It's bright. It's literally a light in the sky. How is it lit up? Explain to me how it's lit up.
Well, because it's reflecting what's showing behind your screen there.
It's reflecting the sun.
Yeah.
Okay, so how come when I look at a rock, I'm standing next to a boulder here on Earth, that's a smooth boulder, and it's kind of reflective. How come it's not as bright as like Jupiter is bright? It's literally like a small piece of the sun. It's like a small piece of the sun.
You know how big Jupiter is.
So you're not explaining how that light's intensifying.
Well, no, it's not intensifying. What I'm saying is you have a massive, massive planet, a planet.
It doesn't matter. It doesn't matter because the sun. Hold on. Let me just finish this point. They say the sun's 400 times bigger than the moon and 400 times farther. Therefore, it's the same size. So if I look at a rock that's this big and I'm 5 feet from it, okay, well, Jupiter is so far away that it looks smaller than that. It doesn't matter. I'm right next to this. The sun is shining on it. It should be blinding me, but it's not. And the sun is closer to this, right? It should be blinding me. That argument alone completely destroys the light in the sky being a gassy ball planet that they tell us.
What are you seeing when you look at it?
As Skylar said before, I don't know. I think it's something to do with creation. I think we're all part of this living system, and those lights in the sky are part of this system. That's why astrology is what the real elite use, and astronomy is for the masses to keep them believing in space.
Well, I certainly don't believe in astrology, but
well, that's of course because you believe in astronomy, which is complete and total hypothetical BS with being nice.
Yeah, but like so Venus, for example, is much brighter than Jupiter. I'm sure you've seen Venus in the morning when it's
I have. I saw Venus last night. It was right next to Mars, and it was also very bright. Now, Venus, you can kind of argue it's closer to the sun and it's reflecting, but Jupiter makes no sense. Jupiter makes no sense.
Well, it kind of because you can't see like Neptune or Uranus with your naked. Well,
because
can,
they're not what they say, right? They're not what they say.
But but then what are they? I guess like if I were to accept they're not planets, then what am I supposed to do?
That's not.
I guess like what
listen,
do you do
I don't
that?
know. I'm not responsible for coming up with the answer when you don't know what something is. I don't have to come up with a replacement model. But if we look at Jupiter, hold on a second. This is what I want to show you. This is from this is from NASA, right? Why isn't it so bright? How did they get it? Did they turn the aperture down?
I would need to know the exact source for that. I don't know.
Actually, I'm sorry, that's the wrong one. That's a pond with ducks.
Nice.
That's not what I was doing.
That's good. Yeah.
Come on. I said you have to have a joke. Okay.
Yeah, that's funny.
All right.
It's even funny because
that's real,
here's Jupiter that NASA has. I'm trying to find the one. Oh yeah. So this is a space probe that took a picture of Jupiter. How did they get? What did they have, a solar filter on there? Because Jupiter.
What did you say took that picture?
This is from NASA, from some Voyager or whatever. Took this 2014 and 2016.
So it was a passing by.
Yeah, but again, you have to believe that this is real, and none of the clouds changed over 2 years. Every cloud is exactly the same.
Are we just gonna breeze over how those look literally identical to the miniature?
That's what we're talking about. the one I just showed.
Yeah, it's identical, and these stuff like this, and Jupiter's not the only one. They have one of the moon too. I've heard that from.
Well, Skylar, they use this picture to make that model. Come on. It's not the other way around. That's crazy.
I do think
you're right.
I do think I don't know. I'd have to look at exactly. I'd have to see what they said about those images specifically to see.
I'll tell you what they said. They found out that Jupiter has a magnetic core because they filmed the Northern Lights.
Yeah,
that's crazy. Come on. Now let me ask a question. Did I put this in there, or did NASA put this in here? Do you know? Can you prove either way?
No, I don't know.
Okay. But
that's
when
what I'm saying.
I'd
have to look at it myself.
So if I put it in there, did I do a good job?
Sure.
Really? That's good. That's believable. So if NASA put it in there, then it has to be real. Do you see the bias that you have?
Not see how I'm not just accepting it though. Like I'd have to see.
I appreciate that.
You can see both of you can go and look at Jupiter and it looks just like that. Is what I'm saying.
It looks just like this. This is the new picture of Jupiter that NASA just gave us. All right. You believe these are paintings.
It actually doesn't look like what you're talking about unless you use some digital imaging and rendering with it, right? You're not going to get Jupiter.
No, that's not true. You can see it.
You can see some blurry. You can see some blurry bands and a little. I'll give you. You can see a little spot and some blurry bands, but nothing to the detail of what NASA's claiming.
Well, with a legitimate telescope, you can with a big Dobsonian 12-inch telescope. It's just purely optics. It just has two mirrors, right? Three mirrors.
Joel.
And it can look like that. You can see it's not just blurry bands. You can see the detail and the red dot and everything.
So Joel, if you do the research and see that the 2014, 2016 photos are both claimed to be from NASA and all of the clouds are the same, what will you do? What's your excuse? What will you say?
Well, I'd have to see what they say about it.
Let's say they say these are two separate pictures. The second one showed that there's northern lights. Okay. What will you do? Because you now have evidence that they're lying because all the clouds are the same. When they show us this, the clouds don't say the same. This is just over a couple of days. Okay. Right. The clouds are moving, right? But they showed us 2 years apart. The clouds are the same. So I'm not saying that, you have to do your own research. When you find out that that is both official from NASA, can you completely say NASA's a complete and total fraud and throw out everything they've ever given you? Or are you going to make it?
Well, I wouldn't go to that extreme because that would be a slippery slope fallacy, which I'm sure you're aware of, Skylar.
But it's
you can't throw the baby out with the bathwater.
But it's the burden of positive claims and letting things pass through the lens of empirical of what can be empirically verified and what can't, right? We keep having to, on the globe side, rely on the story from people who came admittedly from Project Paperclip. If you don't know anything about that, you should definitely look into it.
No,
I
know about it.
Yeah, it wasn't just America though. That's actually what people don't understand. It was America, China, Russia. It was all the big countries took the Nazi scientists and then you employed them in their own scientific programs, not just the space program, right? So for us to just blindly agree that, okay, what they're giving us is factual when they do show us like horrible footage like this, like you can make stuff like that super easy today, and all you need is a little bit of theater magic to do it back in the day, right? If you take in even 1 year of stagecraft, then a lot of the magic of NASA just kind of falls away.
Yeah, I think again, well, I take things on a case by case basis. So like, I'll look into the mountain things. I looked into the inverse square law thing. I'll look into the high pressure versus low pressure thing, and then I'll look into the 2014. So did you make those images, or
no? Those are from straight off of NASA's website.
So you didn't make those. Okay. So yeah, I'll look at those and I'll see what they say about them, and then I'll also reference those against other amateur images that we have. But yeah, no, Skylar, I did need to make sure that you understood that we can see Jupiter with a significant amount of detail just with.
So yes, let me point that out. Yes, you can. And Jupiter is actually a train with 8 different lights on it. Okay. I mean, you don't know what Jupiter is. You can see it. It doesn't mean it's millions of miles away, that it's a giant gas ball made of helium that has more gravity than all of the other fictional planets. Okay. You're believing a story and using it to reify your belief. Basically.
Yeah, I guess in general, but doesn't mean the story is necessarily false, I guess. So we all accept a narrative perspective of reality ontologically.
Okay,
so
quick question.
You have to start somewhere.
Quick question about Jupiter for clarification. The method that you use to get the clear picture of that, is that similar to the method that you use to also get the clear pictures of Neptune? Where you have to allow so much photons to come in to build out the picture, and so it doesn't give it
long
to you.
Exposure.
Yeah, exactly. It doesn't give it to you instantaneously, right?
No, I'm saying with a big enough telescope, if you're getting a picture, it's different. But if you're using a telescope for direct observation with your own eyeballs, or even directly into a camera, you can see a significant amount of detail, like Dave said.
So I mean,
and
I guess
then you can also see its moons around it.
I can agree. I'll even give you the moons. I've actually seen amateur photographers with cameras take pictures of the moon. So I'm not saying that you can't see that. Again, I was talking like the insane detail that you're seeing between the different colors in the clouds. Like that only comes from NASA. And anytime that I've ever seen anything like that from any amateur was because they had the long exposure. They had it digitally rendering through a computer. And in my mind, there's no way to verify that the program, the software, is not actually just building the image of what it is expecting to see.
I mean, I'm sure you could do it yourself and try it. I have an astrophotographer friend who took it up in New Mexico, and he's
like
done it himself.
Build the software from scratch and everything, huh?
Well, I don't think the software's biased. It only takes in what you puts out what you put in, I guess. It's not going to do something so like off, where it just flips from one image to another. You have to meticulously yourself hand.
Well, if I was just saying, if I was at the top and I wanted people to believe in this thing, I could potentially put out a program that just gives people the proper, quote, correct images of what they're supposed to see. You wouldn't expect it to be off because it's programmed to be right. But I'm not a coder. I wouldn't,
Hey, Dave, I think is one of those things that that's put in there. I think one of those. So those are actual objects. I think that it's using, right? At least that software. It's using actual images of things, is it not?
No.
It's all CGI, all of it. It's using CGI images as CGI images.
Oh,
Okay,
I see.
you
Okay.
you believe that they're all real.
Oh, I can't really
So,
tell through the
no,
thing. I was just
I once
curious.
took the deep star field that they did a time lapse, of a piece of the sky the size of a grain of rice, and they saw like a million galaxies. You know what I'm
Yeah,
talking about,
10,000
right?
galaxies. Yeah.
Yeah, 10,000 galaxies. I took that and I put it into my film editor, and I zoomed all the way in on the smallest area I could, and then I did the effect where it just starts panning out slowly, and I made like a 30-second video of it just panning across, and the stars are going, and then I posted it. So it looked like it was from NASA. And I got into a week-long argument with Globers saying that no, it's real, and telling me how they did it and everything. And then finally, when I revealed it, they all went silent on me.
See,
So
it's kind of funny because on Facebook, I'll call out. There's a lot of space. Well, this probably sounds funny coming from me, but there's a lot of legitimately fake space stuff that comes out, and I'm always the first guy to comment that, and everyone's like, oh my gosh, it's so beautiful. I'm like, wow. It's like, no, this isn't real for X, Y, and Z reasons. And
It's
you're
a big
halfway
niche
there.
it's a huge niche that's actually muddying the waters quite a bit.
yeah, it's really unfortunate for, I think, both of us, honestly.
Well, we're not
Because
the ones with
it's
the honestly, it's not so much of a problem for us because we don't have the positive claim, right? We're not claiming that the Earth is a curving, spinning, wobbling, tilting space ball, which I mean, we didn't even get into since you brought up rotation was brought up briefly. I mean, we didn't even get into all the different wobbles that the Earth has been experiencing over the last several years that they've predicted or is somehow required for the model to work, including
yeah,
the
we could get into that next time.
yeah, for sure.
So I want to bring up one thing. They have Earth-based telescopes here that take these deep field images, and when they took the deep field image, they said that the telescope is mounted on a cement block that's 10 feet thick, a huge cement block, and it's perfectly leveled or whatever. And the operator during this 10-hour exposure has to walk around in socks because the vibration of his shoes could ruin the entire exposure. Right? You've seen the documentaries on that, yes?
I didn't watch the documentary.
Yeah.
Yes.
So they talk about that, but then you have to say, well, while he's worrying about the vibration of his feet, the Earth is spinning at 1,000 miles an hour. It's orbiting at 66,000 miles an hour. It's chasing the sun at 500,000 miles an hour, and the entire galaxy is moving sideways at millions of miles per hour. And how does the tiny vibration from his foot make a difference? And then you look at the Hubble. The Hubble telescope does these long images too. It's doing everything that the Earth is doing. Also, it's traveling 17,000 miles an hour around the Earth while the Earth is going around the sun. So it's moving in 5 different directions at once, and it's able to hold itself steady on a grain of rice-sized piece of the sky to take a deep field image for hours and hours. I'm sorry, that's a religion. That's a ridiculous story.
Well, what's the explanation that you've heard for that?
The explanation is it's fake. There is no Hubble telescope.
No. What is the explanation?
They won't address it. They don't address it.
Oh, no one's addressed that with you?
No one will address it. I know
I could
exactly
address
what
that
they'll
with you
say.
next time too.
I know exactly what they're saying.
Yeah, so that's what I'm
perfectly,
asking.
or it's perfectly orbiting around the Earth. It's perfectly matching the spin of the Earth, the orbit of the Earth, the speeding up and the slowing down of the Earth. I mean, it's insane.
So I guess the question is, why would I don't want to get into this now. We could do that next time because that's another whole topic. So what just like Earth's rotation, I guess we could get into that next time.
Well, you can, but no one's ever measured it. Okay, no one's ever.
No, I'm saying an explanation of why you wouldn't feel it and like how that all would work, like the mechanics of that.
Well, that's the thing. Like you can explain away the observations literally all day.
Yeah,
long.
but what's the counter explanation? I guess like what's wrong with the explanation?
Oh, well, here's the thing. It's explaining why we don't experience any movement. I don't need to explain like a problem with that. It's explaining away an observation. The observation is that we aren't moving, but your side wants to invoke that we in fact are. So in order for that, you have to beg the question and create a mechanism for that. We have no need to do that because we're not asserting that we're moving.
Yes, but you are asserting that it doesn't make the explanation doesn't make sense. And what I'm asking is, what about the explanation doesn't make sense? But that's what I would like to get into probably in a future
That's fair.
podcast because it has been 2 hours. If you
All
guys
right,
didn't
Joel.
realize.
Any final comments?
No, I mean, I think it was fun. We touched a lot on a bunch of different things. A lot more than I think I expected. But I think it's fine. I think it was a fluid conversation. We were never bickering or like kind of.
If you had to pick your one best proof the Earth is a globe, what can you pick one or?
I would say the celestial movements. Yeah.
The movements of the lights in the sky that don't
Well,
make
you
any
could
sense.
call them lights in the sky, but you know.
Yeah, you can call them stars
But
that trillions of
no,
miles away.
you
That
guys,
that
you did,
it
you
was
guys did
infinite
acknowledge
brightness.
that it did make sense on a globe if the globe is real.
No,
So
we acknowledge that some of the movements could make sense, but we wouldn't be able to observe them because we'd all be dead, right? And you're. I'm going to think about it because it's amazing that light gets dimmer and dimmer and dimmer and dimmer until it just gets to that dim point, and then it just goes forever. It's amazing.
well, why would
Amazing.
you expect otherwise? I guess like what's
Because
stopping
light
it?
spreads out and it keeps spreading out until it's so dim that you can't see it, and that happens very quickly.
Well, yeah, till your eyes can't see it, but it's still there. Like if
But we
you
can
were
still.
to take a
So
long
how are we
exposure
seeing
photograph,
stars that are hundreds of trillions of miles away?
hundreds of so like in a galaxy or something.
No, like stars in our solar system.
Stars
Well,
in our
100 billion miles away, whatever. We can see other galaxies that are 200, as you said, 200 light years, right?
Andromeda is 2 million light years away. 2.4.
2 million light years. How many miles is that, dude?
Well, so I guess what's stopping those photons from that galaxy of coming to Earth?
They're not nothing. They spread out. They spread out. They spread out. They spread out. They like this intensity of light here, 10 feet away, it has to spread out and fill this much area. And then 20 feet away, it has to spread out and fill a bigger area. And it becomes less and less and less.
Right, but it doesn't become non-existent, I guess. It doesn't go. It doesn't.
It just goes forever, and you can see things trillions of light years away.
But what's wrong with that? Like what? You know,
it's because it makes no sense. That's why.
Why doesn't it make sense?
No, here's what doesn't. This is what doesn't make sense.
How big can you blow up a balloon before the plastic's gone? Can I blow it up forever? Because the balloon's going to get thinner and thinner and thinner. But in your world, after it gets to 10 feet wide, it can go to 1,000 feet wide and 1,000 miles wide, right? At 1,000 miles wide, you couldn't find the surface of the balloon because it would be gone. Just like light, just like sound.
What were you going to say, Skylar?
If the photons are spreading apart, then at what point are the photons so spread apart that there's not a photon to hit your eye?
If it's not that it's because of the nature of light that's hard to answer because you got to think of like just a rays of spherical light coming off of something.
Is light photons? Is light photons?
Yes.
If there was no photons hitting us, thered be no light, right?
Correct. Yeah.
Okay, so you have a surface of a star and it has X number of photons on it, and as that expands, those photons that are all side by side, they're all touching each other. They get more and more spread out, exponentially spread out. Okay. At what point will a photon completely miss Earth?
I'm not sure. I don't know.
It's not far at all. Do the math, and you'll see that it's not far at
all. What I was going to say is I think it would have to be a pretty far distance, and I think the math would reflect that.
Like what, 100,000 miles?
The problem, Dave, and I say this with charity and respect, but even if I did do the math, it's almost a waste of time. And you know why? Because once I present the math to you, it's like there's nothing I can,
Math is not empirical evidence. Math is not empirical evidence.
Yeah.
Let's try to keep our feet on the ground.
It's not charitable to say do the math when you won't.
Well, I'm saying if you do the math, it won't work out because the photons are become too far apart. Okay,
well, that's what you said about the inverse square law, and it did work out.
Well, no, it worked out in math. All right, you're right. It doesn't work. Let's just stay here on Earth. Explain the observation away of the mountaintops. There's no curvature calculator. Even the worst Globee Pro calculator puts the tops of those mountains 20 miles below the curve.
No, I'll look into it. I'll see.
Okay.
Whoever this other Joel guy was, you seem to want him to
Oh
check
my
it
God,
out.
we had
So.
it was yeah, there was two Joels, and it was crazy. It was
That
crazy.
was funny. But
All right,
all
all
right,
right.
yeah.
Thanks, Ben.
Yeah, absolutely. It's
All
been
right.
fun. Nice to meet you, Skylar.
Yeah, Joel,
It's a
thanks for
pleasure.
coming on. It was very nice to meet you. Just to let you know, if you ever want to dip your feet in this again, I do an open panel usually tonight at 10 p.m., but we did this instead. So I was definitely happy to change it up a bit, give the audience a little something different. And I know
What's
that.
your YouTube? You got YouTube? I'm
Yep,
assuming?
Troubling Tribune.
Oh, it's just troubling. Okay, cool. All
Yep.
right.
Yep, simple.
Well, awesome. Yeah, I hopefully it was sort of productive. It's swapping perspectives and whatnot, and giving our sides, and that's what we were here to do. So,
Absolutely.
All right.
hope you guys enjoyed it.
If the Globies, anti-flat earthers, could be as nice as you, well, life would be amazing. Life is amazing.
Certainly,
It'd be more amazing.
That's Dave. That's why I told you I even started doing this in the first place, seeing how you were treated.
The problem is that
right.
there's anti-flat earthers that will literally make just bad, bogus arguments that now genuine people digging through this stuff have to then peer through. And unfortunately, it can be kind of easy to fall into the bad information. So,
well, that's on both sides, I think, for sure.
Absolutely.
So,
on any side, you're going to have misinformation, as it will. So, always important to do your own research.
It's getting worse. Yeah, I agree. I'm a strong proponent of that. So, alrighty, guys. Well, you have a blessed night. I actually like your shirt, Dave. That's actually kind of cool.
Thanks. You can say something on the back, does it?
No. That's...
You can find that on my new T-shirt shop on the flatearthpodcast.com. Hit the shop.
Oh, you made that shirt. Nice. Okay.
Yeah.
Nice.
I have a whole bunch of new shirts and new printer. They're much higher quality printing, and they're awesome. So check out the shop, everybody. It's also on your app in the shopping cart button.
Nice.
All right.
Alrighty, guys.
Everybody go check in your app, and if you don't have it yet, you're definitely going to want to go to the Flat Earth, Sun, Moon, and Zodiac Clock app by Blue Water Bay and use your referral code Tribune so they know that Tribune sent you.
Yeah.
Nice.
Also glad that we were all able to avoid the ad hominem fallacies. That's always nice in any kind of disagreement.
We almost poisoned the well a few times, but I think we did a pretty good job.
Yes, I agree. So anybody who's wanting to comment or whatever, I ask that you just please, be respectful of everybody.
The chat was actually pretty was okay. Flat Earthers are some of the they could be quite passionate. They become passionate, and I used to do it too. So sometimes I do too.
Alrighty, guys. Well, you have a blessed night.
Alrighty. If you want to check out the outro, we're gonna play some an epic outro on our way out. So for you guys just joining us, if you want to stay for just a moment, it'd be absolutely awesome. Dave, did you have anything else that you wanted to add on before we call it a show?
No, that's it. I'm good. Thanks.
Awesome, man. All right, you guys have a wonderful night. I will see you on the other side. Peace.
Peace out.
All righty, guys. What an awesome conversation that we just got to have there. Let's move it on over back to where the heck is the theme page? There we go. Perfect. Awesome, man. Joel does indeed love space, but we definitely liked having him on. Great conversations. Hopefully we can have him on again and continue on. Maybe go for a trilogy of sorts, if you will. But while we go ahead and wrap it up, I do want to shout out just a couple people over in the Rockfin side as well as the YouTube. Been doing a lot of work, keeping it real busy. We got 25 legends over there supporting on Rockfin. There is a link in the description if you guys would like to subscribe if you have an account already, or if you don't, what better time to go and check it out, right? There's tons of content creators out there doing some great work. There is Jaronism, Karen B, Mark Sargent, myself, Mellow Dome, and many, many more. So if you want to know, you really got to go. But to shout out just a couple people, we got Willie, Nanny, Lord Byron, much love, as well as Fishhead Montana and Lord Byron, Roger Meadows. Alrighty. Lots of back and forth. I'm not going to try to scroll through the whole thing. John Osborne. Awesome. If I missed anybody, I'm the you are still appreciated. All right, let's head on over to the YouTube. All right, many thanks, Skylar. This was a great stream. Thank you, Benny Boy. It was a lot of fun doing this. We got Jesse Palmer, True Niece, Singeman, Lord Racer, DITRH. It's hard to pronounce DITRH, so you just naturally want to say Dirt because of all the anti-flat earthers out there. I do apologize. We also have JK, Jess Palmer, Sovereign Soul, Unchained Mind, Dr. Law. How is it that you are not a member? That's crazy. We have Justin Johnson just giving out tons of memberships. Absolute legend, putting the entire tribe on his back. We got Chillin, Joshua, Sarles, Thrash, List, Smith, Bill Wheel. By the way, we also have a members-only stream coming tomorrow night at 10 p.m. We are doing an Ask Me Anything, and I will be joined by my lovely wife, MrTribune. So it'll be a nice chance to get to know us a little bit better. Only have the members chat and members only viewing to avoid the trolls. But we do appreciate everybody being a part of that. So if you want to join up, now would be a great time. Also get your absolutely sick emojis. We got the mind murked emoji and the True Earth cosmology. There's many, many more. As you know, one way to know, and that's to go sign up today. Rob Glow, much love. Mellow, awesome. Rob Glow and Mellow. Martin Haley. We got Shifty Eyes, Shady, Donald Piaskic. Welcome to True Earth. Awesome. Sunglasses emoji. MrTribune, what is up? Oh man, I can't pronounce that. Earthica Stashi. Probably butchered that. Sorry. Joshua Sarles again. Justin Johnson. What is up? It's twice. That's super funny. You guys are awesome, man. All right. JK, I want to see a flat beard on Dave Weiss. How many votes did we get in for that? How many threes did we have in the chat for Dave Weiss growing out a beard? That'd be pretty interesting to see. All right. So if I am missing anybody, again, I do apologize, but there's so much back and forth. So it is what it is. We are going to go ahead and get things closed on out, but it is taking me just a minute to find what I'm looking for. Where? All right, guys. Much love to all the supporters, all the love, all the thoughts and prayers. We do appreciate it. And I will be seeing you guys either later tonight, right? For Witsit's got a show going on. We'll be in the chat. We may join the panel. Who knows? We'll see what goes down. And then we will also see everybody tomorrow night for the members only stream. It's going to be awesome. But until then, I wish everybody a wonderful night, morning, evening, regardless of where you're at on the plane. And I'll see you then. Peace.